So this will be the video solution for questions 18 to 21 on the 116 exam 1 from winter 21. And these three questions we're looking at the tutorials on the superposition and reflection of pulses, SPR, and reflection and transmission, the RNT tutorial. So the questions 15 to 17 we're looking kind of combining the simple harmonic motion tutorial as well as the same material from the lecture on simple harmonic motion. So this is looking at this tutorial number 2 and tutorial number 3. So let's look at the first question, and I think I'll do a sort of a broader sort of discussion of this question to go through the key ideas. So two springs are connected at junction J. You're not told which spring has a greater mass per unit length. A student generates a pulse at one end of the connected springs. The shape of the springs a short time after the pulse has reached the junction J is shown below. Which of the following statements must be true? So I'll go through sort of the two scenarios, and sort of, because I think in the other version, the second version was the opposite of this, so I wanted to sort of do a slightly more general solution to what we, so we can deal with both scenarios, whether it's the initial pulse is generated in the more dense spring or the less dense. So let's imagine we have a pulse that is moving in a, let's say, a light material towards a heavy chain. So this, in a sense, is going from light to more dense. So so light sort of maybe fishing line towards a chain. So in this particular example, this particular end, the boundary is going to behave as a fixed end in this scenario. So in a fixed end reflection, we expect to get an inversion of the the reflection will be inverted compared to the incident, and then the transmitted will of course have the same shape as the incident, but is in a sense it will be on the same side of the spring, but it should be slightly shorter because it's moving slower in the more linear mass density material, and it should be closer to the boundary than the reflected. So I expect the reflected to move. I'll draw it over here. Let's say the reflected, and the reflected should be same width as best I can draw it there, and in the more dense material, it should be closer to the boundary, same side, but slightly and somewhat narrower as best I can draw it. So key things here is the transmitted narrower and closer to boundary. So we know it's moving slower in the material. So the leading edge of the transmitted and the leading edge of the reflected are created at the same time, but they move at different speeds. The one in the lighter material will move at a greater speed. So the reflected pulse, this should be inverted and same width as the incident. So I'm sorry, this narrower here is since narrower than the incident, and it'll also be narrower than the reflected. The reflected has to have the same width because it is moving in the same material, and the time interval that's created, the reflected is created as the same time interval that the incident was created. So they should be sort of identical in width. There should be a slight decrease in the amplitude because the initial energy of the incident is sort of divided up between the transmitted and the reflected, but we don't get into too much detail on the amplitudes. Okay, so that's looking at fixed end. So suppose that we sort of reverse this and we send in a pulse on the heavy chain. So maybe I should just add a little bit of detail here. So this is the incident. This is use R for reflected, T for transmitted. That's heading in that direction. The reflected head is heading in this direction. Here I'm going to send in the incident on this one toward the left, towards a light string. So this time the boundary will behave as a free end. Okay. So what we expect here, again, in this case the transmitted should be further from the boundary than the reflected, because it's going into the faster moving sort of, it'll have a higher wave speed, it'll be on the same side, and it should be wider. So I'm trying to draw this, oops, trying to draw my lines here. So we're looking for a wider pulse here, and farther from the boundary. And then on this side, we should get a reflection on the same side, and it should be closer to the boundary and the same width as the incident. So same width as the incident, and then closer to the boundary than the reflected, or sorry, the transmitted. Okay, so that's sort of our discussion of the two scenarios, whether it's coming in on the light material and we toward the more dense material and we're treating the boundary as a fixed end, or whether it's created in the heavier material going towards the lighter material, creating a sort of a free end. So let's think about the characteristics, the features that we have. So when we have a fixed end reflection going from light to more dense, the reflected and transmitted are on opposite sides of the spring, or the string of the material. For the free end reflection, the reflected and the transmitted are on, sorry, this is the transmitted here, this is the reflected. Let's add those details just now that I'm talking. This is the reflected, this is the transmitted. They're on the same side when the boundary acts as a free end. So and I think that's what I meant in the opposite version. So I think the other version might have had them on the same side. So, but hopefully this will be able to, you'll be able to tell from both of these. So from this particular example, we've got them on opposite sides. So what we do know from this question is that this must have acted as a fixed end. If they were on the same side, it must have been acted as free. So that's one thing that we know for sure. One easy thing to tell from the figure is that the wave speed and the right spring is greater. So we can see that the distance traveled from the boundary of the leading edge of this one is larger than this particular distance. So I definitely know that the wave speed on the right spring is greater. So again, you can just look at the distance traveled by the leading edges of the transmitted and reflected to tell the wave speed, because the leading edges are created at exactly the same time. The mass per unit length on the spring on the right is greater than that on the left. That's a statement that's incorrect. So we know that wave speed is inversely proportional to the linear mass density. So V is inversely proportional to mu, square mu of mu, because we know the tensions are the same in both strings. So 2 is not a correct statement. Okay, so we know that actually, if I write this, if this is mu left and this is mu right, I know the correct statement is that mu right is less than mu left. And so so the one on the right is the lighter material. So then the student generated the pulse on the right end. So if we have a fixed end reflection, okay, to get a fixed end reflection, you have to have the incident pulse created on the lighter material, in the sense the lower linear mass density. So that's in this particular case. If you have a free end reflection, the incident pulse has to be created in the material that has a higher linear mass density. So in this particular example, the student would have had to, since they're on the reflected and the transmitted on opposite sides, the student would have had to generate the pulse in the lighter material, which is the spring on the right. So they're the two correct statements. There's two correct statements in this case, 1 and 3. So that's typed here. Okay, yeah, I think hopefully that addresses enough of the logic for the second version. If not, please get in touch. I'd be happy to walk through the reasoning. Okay, let's go to question 19. So that's just the second page. Okay, so question 19 is looking similar sort of kind of question. So use the setup for the next two questions. There was a sort of free response question. So students want to each generate a single transverse pulse by moving the ends of a spring at unknown times. Originally there was a line of cups distance d away from the spring as shown below. Each pulse was generated on a single side of the spring, either the top away from the cups or bottom toward the cups. After the pulse is generated by both students have travelled down the spring, only 2 of the cups were disturbed as shown. Ignore reflected pulses. Okay, so which of the following statements must be true? So we can see that here we've got 2 disturbed cups closer to student 1 in this case. I think the second version had them closer to student 2. So in this particular case, both pulses were generated on the bottom of the spring. That would have to be true. So as noted here, each pulse was generated on a single side of the spring. So if we created 2 pulses on the top side of the spring, and they were moving towards each other, they're not going to disturb any cups. So so the top won't work. So but in order to disturb cups on the bottom, they would have to be created on the bottom. So that is a correct statement. So I'm trying to raise that. So yes, we would have had to have 2 pulses created on the bottom of the spring. So that is a correct statement. Both pulses have a maximum absolute displacement less than d. That's true. If either of the pulses had a maximum displacement greater than d, all cups would be knocked out. So since only 2 of them are knocked out, both pulses have to run underneath the cups, but at some point they're going to overlap, create constructive interference, and knock out a small number, in this case 2 of them. So the sum of the maximum absolute displacement from both pulses is greater than d. That is true because we know that they constructively interfere at some point, knocking out 2 cups. They move through each other, coming back down below the sort of distance d, and leave the rest of the cups undisturbed. So for the question 18, all of the statements are correct. So that's so they're definitely generated at the bottom, otherwise we wouldn't disturb any cups. They have an absolute displacement less than d, otherwise we would knock out all cups. And there's some of the maximum displacement is greater than d, again it would have to in order to knock out 2 of the cups that are shown. Okay, I think that's the same for both versions. Okay, not to include question 20, I did. Okay, so question 20, and so it's the same sort of setup here. But this was an explain your reasoning question. So for the pattern of disturbed and undisturbed cups in the previous question, which of the following statements can you conclude are correct? Explain your reasoning. So we can see that in this particular version, the disturbed cups are closer to student 1, and than they are to student 2. And we've sort of previously concluded that both pulses are on the bottom of the spring, and we're disturbing the cups closer to student 1. So that means that student 2 would have had to create the pulse at an earlier time. So student generate the pulse after student, yes. So if we're talking student 1, so student 1 goes later. So student 2 creates their pulse, it's moving along, then student 1, to create them at the same time, we'd expect the 2 cups in the middle to be knocked out. If student 1 created it first, we'd expect cups to be knocked out closer to student 2, which I think might have been in the second version. But since the cups are knocked out closer to student 1, we expect the pulse from student 2 to have moved some distance before the pulse from student 1 is created, such as to knock out the cups closer to the student 1. And we also know that the speed of the pulses is the same because of both, they're also moving in the same material. So that's sort of a key piece, is that both pulses move at the same speed because they're moving in the same medium. The cups that are disturbed are closer to student 1, which means that student 2's pulse would have had to sort of have some time to sort of move a little bit of a distance, because once their pulse are created, they move at the same speed. So to disturb the cups closer to student 1, student 2 has to go first, or student 1 has to go later. So student 1 is generating the pulse after student 2. Okay, so that's that was question 20, and then the last question on the exam is looking at this particular question. Okay, so we've got a pulse moves with a speed of 10 centimeters per second to the right along a spring. The shapes of the springs, spring at times t equals 0 seconds, t equals 4 seconds are shown. And okay, and then is the right end of the spring a fixed end or a free end, or can it not be determined? Explain the reasoning. Okay, so in this particular scenario, what we see is that the incoming incident ray, sort of incident sort of pulse, it's got sort of two displacements that are negative, one in the vertical, but in a sense the what we have sometime later, in a sense, is a pulse that is below the equilibrium point. So if we think about the options for the sort of phantom pulses, so if we think about if fixed, what would the phantom pulse look like? Well, in a sense, we have a mirror image through the vertical and another mirror image through the horizontal. So the fixed, if it was a fixed end, our phantom pulse, I'll just actually draw the full line here, would look like this. Okay, so, and then where would this pulse in a sense be 4 seconds later? So the leading edge here would be 1, 2, 3 would be over here, and we can think in a sense that this particular point here be 1, 2, 3 would be back over here. So we would have a sort of a leading edge of the sort of phantom would be here, and then the other part of the pulse, the actual instant pulse, would be here. So I would expect something like this if it were fixed. So it's in a sense, because it looks like, it doesn't look that it is a free end. So in a sense, if I think about what this sort of phantom would look like, so we know in the fixed end we sort of get an inversion of the incident pulse, and so since here we're not getting a sort of an inversion, we're getting essentially the reflection that's coming on the same side, it's actually a free end. So that's sort of, you know, looking at that in more detail, if I think about if we were just to think little more loosely, in a sense of thinking that if it was a free end, what would the reflected end up looking like? Well, it would be an inversion. So we would expect this would be the reflected for if fixed end. But if it was a free end, which it is, then the reflection will be sort of the same. And that's sort of what this part is sort of indicative of, is that this is part of the reflection for the free end. So I can, that would be sort of enough sort of to recognize the sort of what type of end this is. So let's go ahead and erase some of this and draw in our reflected pulse. So based on that reasoning, knowing that it is a free end, so then our phantom pulse would look something like this. Okay, so that would be at t equals 0 seconds. Then if I move, this particular point 1, 2, 3, 4, so that's this piece here. So the phantom has come out to here, and so I'll draw in the phantom in green. And then maybe just to overlay that on top of the incident. So the peak of the incident, so this point here, which should be this particular point, so this would be the red, and then to here. So these 2 points here, the upper part of the green of the phantom, sort of overlapping with the last piece of the incident, basically sum to give us this flat line of 0, and then the sort of leading edge of the phantom is giving us the actual shape that's below the equilibrium, and this would only happen if the end was free. Okay, so that's sort of what sort of linked to question, I didn't actually add in 22. Oh yeah, so you're basically asked to explain, so that's sort of what I was working through, those sort of points there to indicate if in a sense, looking at the sort of the fact that the reflection is on the same side of the medium as the sort of as the incident as we would expect for a free end, that certainly leads us to think about the free end. And what we're getting, the actual pulse itself is the sort of the interference, or in a sense, yeah, so the superposition of that incident with the sort of free end phantom pulse to give us sort of this leading edge piece here below the equilibrium point, and then sort of that the middle piece of the phantom overlapping with that sort of the last piece of the incident, giving us that 0 displacement toward the actual boundary. But this boundary is definitely behaving as a free end. Okay, I'll wrap up the that's what wrap up the question. That wraps up the whole exam. So yeah, if you have any questions, please let me know. Encourage you to post your questions also to Slack, to the exam channel, and I can keep an eye on the questions there. Okay, I'll wrap up the video there, and keep an eye on Slack for any questions.